Welcome and good morning. Myself G. Sivaraj, full-time research scholar, Department of Electrical and Electronics Engineering, Government College of Engineering, Salem. In today's session, we are going to see the MATLAB simulation of three-phase full-bridge inverter. Essentially, an inverter is a power electronic circuit that converts DC power into AC power at desired output voltage and frequency. The basic three-phase inverter is the 6-step inverter in which 6 switches are used and each switches are triggered at a regular interval of 60 degree in a proper sequence. Majorly, the three-phase inverter can be divided into two based on the conduction modes, that is 180 degree and 120 degree conduction modes. Now let's see the aim. The aim is to simulate three-phase inverter in 180 degree and 120 degree conduction modes. Software used is MATLAB Simulink. Formula used is for 180 degree conduction mode, RMS value of the line voltage is √2 divided by 3 Vs. RMS value of the phase voltage is √2 Vs divided by 3. In 120 degree conduction mode, RMS value of the line voltage is Vs divided by √2. RMS value of the phase voltage is Vs divided by √6. Now let's see the operation of three-phase inverter. This is the schematic of the three-phase inverter. Here 6 switches are used and these switches can be grouped into two, that is upper group and bottom group. In the upper group, the switches are named as S1, S3 and S5, and in the bottom group, switches are named as S4, S6 and S2. And each switches shall be triggered at a regular interval of 60 degree in the numbering sequence shown. For instance, switch S1 is triggered at 0 degree, the switch S2 which is present in the bottom group is triggered at 60 degree, then switch S3 which is present in the upper group is triggered at 120 degree, then switch S4 which is present in the bottom group is triggered at 180 degree, then switch S5 which is present in the upper group is triggered at 240 degree, then switch S6 which is present in the bottom group is triggered at 300 degree, then again the switch S1 which is present in the upper group is triggered at 360 degree. This is how the triggering sequence shall be followed for both 180 degree and 120 degree conduction mode. Now let's see the operation of three-phase inverter in 180 degree conduction mode. Here at any instant, any particular switch will be conducting for 180 degree time period only. For instance, the switch S1 which is present in this branch is triggered at 0 degree and this will be conducting for 180 degree time period. Then after 180 degree time period, switch S1 is turned off. Then after 180 degree time period, the switch S4 which is present in the same branch is triggered and this will be conducting for 180 degree time period till 360 degree time period. Now let's see the operation in detail. For instance, the switch S1 is triggered at 0 degree, then switch S3 which is present in the other upper group is triggered at 120 degree. Then after 240 degree, switch S5 which is present in the upper group is triggered. This is how the triggering sequence will be followed for the bottom group also. For instance, switch S4 is triggered at 180 degree, then switch S6 is triggered at 300 degree, then switch S2 which is present in the bottom group is triggered at 420 degree. Also, at any instant during the operation, 3 switches will be conducting, that is, 2 switches can be in the upper group and 1 switch can be in the bottom group, or else 1 switch can be in the upper group and 2 switch can be in the bottom group. Now let's see the operation of three-phase inverter in 120 degree conduction mode. Here at any instant, any particular switch will be conducting for 120 degree time period only. That is, if switch S1 is triggered, this will be conducting for 120 degree time period only. After 120 degree time period, this will be turned off. Switch S4 which is present in the same branch will be triggered after 180 degree time period only. So once it is triggered, this will be conducting for 120 degree time period, that is till 300 degree time period this will be conducting. So after 300 degree time period till 360 degree time period, neither S4 nor S1 will be conducting. So this is how the triggering will be followed for the other branches also. This is the only difference between the 180 degree and 120 degree conduction mode. However, the startup triggering or the triggering sequence is common for both 180 degree and 120 degree conduction mode. That is, if switch S1 is triggered at 0 degree, then switch S3 which is present in the upper group is triggered at 120 degree. And switch S5 which is present in the upper group is triggered at 240 degree. So this triggering is same for both 180 degree and 120 degree conduction mode. and during the operation at any instant two switches will be conducting. That is, one in the upper group and one in the bottom group will be conducting. Let's see an example. Here from 180 degree time period to 240 degree time period, S4 and S3 are conducting. That is, S4 which is present in the bottom group and S3 which is present in the top group is conducting. Now let's see the tabulation of 180 degree and 120 degree conduction mode. Here the output parameters shall be measured and these parameters shall be compared with the theoretical value. This is the MATLAB workspace. This is how the opening page will be looking like. Now we want to open the new workspace to draw the schematic and run the simulation. First let's click the new. In a new tab, Simulink model will be there. So we can either click Simulink model here or we can directly click the Simulink model here. So once this is selected, different controls will come. The blank model can be selected. So once this is selected, so we will get the blank workspace like this. First we will name it. So this can be saved according to our simulation model. Now the file is named as IGBT based PWM 3-phase inverter. These are all the components that we need to run the simulation. Let's see the component one by one. So this is the DC voltage source and this is the pulse generator block to give the pulses for the IGBT or the MOSFET switch. This is the IGBT switch. Here we need 6 IGBTs. So by selecting one IGBT from the library browser, we can duplicate it by right clicking it and dragging it. So like this we can drag it and duplicate it. Then we need a 3-phase VA measurement to see the phase voltages. Then we need DMUX block. We need scope. So this is similar to the CRO in our practical lab. Next we need the load. So here we need resistive load. The series RLC branch can be brought in and changed it to resistive load. And this is the voltage measurement block. And this is the scope block. This RMS block is needed for converting the instantaneous voltage into RMS voltage, and we need a ground block to connect the common point to ground. Next we need a power GUI block to run the simulation. Now let's see how to select the components from the library browser. So this is the library browser. To bring in the DC voltage source, we can type in as DC voltage. So this can be right clicked and added, and we need pulse generator block. So we can type in as a pulse generator. So the pulse generator which is coming under Simulink can be taken. Then we need IGBT. The IGBT which is coming in a Simscape can be taken. This can be right clicked and added. Next we need a 3-phase VA measurement. So 3-phase VA can be typed in. This can be right clicked and added. Next we need a DMUX block. We can type in as DMUX. The DMUX which is coming in Simulink 2 can be taken. To select the RMS block, we can go in Simscape, under Simscape Power Systems, Specialized Technology, Control and Measurements, and Measurements. In Measurements we can see RMS block. So this can be right clicked and added. Next we need a ground. So we can type in as ground. The ground which is coming in Simscape can be taken, and we need power GUI. So this can be right clicked and added. Once all the blocks are brought in, we need to set the parameter values for those blocks. For DC voltage source, we can double click it and we can set the value as 230. In IGBT, the default values can be kept, and in 3-phase VA measurement, the voltage measurement shall be phase to ground. So this will measure the phase voltage. And then the series RLC branch parameter can be changed. This branch type can be changed as R to mention this as resistive load, and then the resistance value can be kept as 50. And then in DMUX block we can double click it. If this is mentioned as 2 ports, 2 output ports, then we can change it to 3, since we need 3 phase voltage need to be measured. And in RMS block, the default values are in fundamental frequency it is 60, so it need to be changed as 50 Hz, and then initial RMS value can be changed into 0. And in the pulse generator block, so we need 6 pulse generators. The IGBTs are named as IGBT1, IGBT3, IGBT5, and in the bottom half it shall be named as IGBT4, IGBT6 and IGBT2. For the first pulse generator, we can set the parameter values as follows. Here the amplitude can be kept it as 1, and period can be set it as 1 divided by 50, and pulse width can be kept it as 50. So this pulse width is going to decide whether our simulation is going to run in 180 degree conduction mode or 120 degree conduction mode. If we want to run the simulation in 180 degree conduction mode, then we have to keep the value as 50 in pulse width. If suppose we want to run the simulation in 120 degree conduction mode, then we have to change the value as 33.33. So this is the value which is deciding whether we are running the simulation in 180 degree or 120 degree conduction mode. Now initially we will run in 180 degree conduction mode, so we will keep the value as 50. So this is the first pulse generator, so we will keep the phase delay as 0. And in the second pulse generator block, the amplitude value can be kept it as 1, period can be kept it as 100 by 50, the pulse width can be 50. That is, the first 3 parameter values can be same as the first one. So these parameter values shall be same for other pulse generator blocks also. This phase delay shall be 60 degree, which means this IGBT is going to trigger at 60 degree. So for setting the value as 60 degree, initially we have to put it as 1 divided by 50 into 60 divided by 360. And in the third pulse generator block, the first 3 parameter values can be kept as other first 2 pulse generators. Then for phase delay, the value can be mentioned as 1 divided by 50 into 120 divided by 360. So this is going to trigger at 120 degree. And in the fourth pulse generator block, the first 3 parameter values shall be same, and in the phase delay it can be changed as 1 divided by 50 into 180 divided by 360. So this is going to trigger at 180 degree. And in the fifth pulse block, the phase delay can be kept as 240 divided by 360. And the sixth block, the phase delay value can be mentioned like this: 1 divided by 50 into 300 divided by 360. In the series RLC branch, values can be kept like this. That's it. Now we will connect all the components together. So we can select one end of the component and drag it and connect it to the other end of the component. Once this is properly connected, the red line mark will change it to black. Once all the components are connected like this, we will have to set the configuration parameters. So by clicking this configuration parameter settings, we can change the solver selection type. Here the solver selection can be variable step, and the solver type can be OD23TB stiff TR-BDF2. And then this Power GUI block simulation type value can be changed. Initially the default type will be continuous. This can be changed to discrete. So now everything is set. We can compile and run the simulation. Here the simulation time is kept as 1, so it has run for 1 seconds. We are getting the RMS phase voltage as 104.8 volts, RMS value of the line voltage as 183.8. We want to see the scope value. This is showing the 3 phase voltages. If we want to zoom in, we can zoom in and see it. If we want to see both RMS and line voltages, we can click this scope block. We can zoom in and see it. So the first top one is showing the phase voltage, and the bottom one is showing the line voltage of B and C. Now we will compare the theoretical value and the simulated value. The formula for the RMS value of the line voltage in 180 degree conduction mode is √2 divided by 3 Vs. It means 0.8165 into Vs. We will calculate now. The source voltage is 230 into 0.8165. We are getting 187.795. This is closer to 183.8 what we have got in the simulation. Since the voltage that we have got in simulation is not a pure sine wave, so the values are closer and not exactly matching. And similarly, the formula for the RMS value of the phase voltage in 180 degree conduction mode is √2 Vs divided by 3, which is nothing but 0.4714 into Vs. Now we will calculate. The source voltage is 230 into 0.4714. We are getting 108.422. It is closer to 104.8 in the simulation value. That's it as far as simulation of IGBT based 3-phase inverter is concerned. Thanks for watching.